Hi everyone, and welcome back to the last week of your artificial intelligence course. You made it up till here, congratulations. This week we'll explore together some aspects of deep learning, which is the state of the art of artificial intelligence today in vision. Deep learning is also a trend today because of its huge progress and also its promise to solve many aspects of artificial intelligence problems. Afterwards, we'll explore together some aspects of robotics. We will have an invited speaker, Professor Peter Allen from Computer Science Department at Columbia University, who will be talking about robot path planning. Finally, I'll be reviewing the main concepts seen during the last weeks and conclude the course. So first of all, deep learning. Deep learning is becoming a kind of buzzword. Everybody is talking about deep learning. And this is actually justified because deep learning has been actually making breakthroughs in the last few years. Deep learning is stemming from neural networks. So remember, we discussed neural networks in the last few weeks. Neural networks, as other problems in artificial intelligence, are inspired by nature. Just like genetic algorithms and other aspects, neural networks are trying to mimic how the brain functions. So this worked extremely well on handwritten character recognitions in the 90s, in spoken words, and in recognizing faces. So this topic was extensively studied in the 90s with a moderate success because we were missing enough computational power and we didn't have enough data. Now, neural networks are back with a lot of success with deep learning, thanks to the algorithmic and also to the computational progress that we have witnessed in the last couple decades. The first algorithm, we discussed it in the last few weeks, is called the perceptron algorithm from Rosenblatt in 1959. More precisely, here is the history of neural networks. These were invented in the 50s and 60s, as I said, in Rosenblatt, with the simplest neural networks, such as perceptron. We have seen in the 70s a slow progress because we didn't know how to train those perceptrons to learn from data. In '86, we witnessed the invention of backpropagations that allows actually to find the weights on a network by doing several batches of learning. So you feed the network, you get some errors, you go back, you backpropagate these errors, and you fix them. And by an iterative process, you can actually finally find the weights. In the 90s was the invention of convolutional neural networks by Yann LeCun, who used them to recognize handwritten digits on envelopes for the US Postal Services. This was a very important moment because USPS has switched from a manual recognition or semi-manual recognition to an automatic recognition of handwritten digits on envelopes. And this has also worked for reading digits on checks. Okay, so then in the 90s, we saw the invention of recurrent neural networks that have seen usefulness in other areas where we need actually to embed some of the output information in the input layer. Starting 2006, neural networks are definitely back with several breakthroughs. Deep belief networks and autoencoders were invented where we could not only use neural networks for supervised and unsupervised data, but also we were able to actually encode and different intermediary layers and train backpropagations on pairs of layers in a larger network. 2013, we witnessed today huge industrial interest from companies such as Facebook, IBM, Google, and Amazon, etc. So why now? Because there is a lot of data out there, and also we do have today enough computational power to train this neural network that have several layers and several units in each layer. And it also turned out to work really well. And we witnessed actually breakthrough results in vision and speech. An important idea in neural networks is how to learn the weights of a network of neurons. In other words, how to do a backpropagation to propagate back the errors when you do the learning. So feed-forward neural networks, as opposed to recurrent networks, have no connections that loop. This is a specific kind of neural nets. Backpropagation then stands for backward propagations of errors, where we learn the weights for a multi-layer network. So given a network with a fixed architecture, that is the number of neurons in input, the number of neurons in the hidden layers, and the number of neurons in the output, we need to find these ways that are actually the interconnections between the different units or the different neurons. So we have seen that we use gradient descent to minimize the squared error between the network output, O, and the ground truth that we have, which is Y. So we have learning data, we know the Y for the learning data, and we will actually contrast the Y of the learning data to the O that is output by the network. So we suppose that we have output, multiple output possibly. The challenge is then to find all the possible weights, to find the configurations of the weights that actually have the mapping between the inputs and the outputs. So one of main observations about backpropagation algorithm is that it does not scale well. So let's illustrate how the backpropagation works. So we're going to have some data in the input layer. So we have an input layer. We have an output layer that is the prediction, and we have a hidden layer in the middle that actually compresses the data and gets extra features from the data. All right, so we're going to put some data in as input. So we have some features that we are going to, feature value that we are going to introduce. So it's going to be feature for the first example, x1. So we have, so it's going to be a x10, x11, x12, etc. So we start with the feature 0. In general, we put this to 1. This is the intercept or the bias. Okay, so the idea is to start with some random weights or some small weights for all these connections. We have also weights here. So when we feed, this is feed forward, when we feed the data on the left-hand side, so data comes in this way, we're going to calculate the output, O, that actually is associated with this data based on this weight. So we're going to do all the work of doing the weighted sum and casting that into the logistic function or the tangent hyperbolic function, etc. All right, so once we get this outcome O, we're going to contrast the O to the Y of this example. So this example has a Y, Y1, and we're going to contrast this to see whether we made an error. If the the network makes an error. If the network makes an error, we're going to backpropagate this information. So we're going to backpropagate the information about the weight and fix them. And the process is actually to iterate over hundreds, maybe thousands of iterations to find a stable value set for those weights. This is how backpropagation works. So we have seen that for one hidden layer, but we could also have two hidden layers. In neural networks, there is a strong theoretical result that states that the universality of neural networks. In other words, there is a neural network for any arbitrary function. This is pretty powerful, and we can even be precise about the number of hidden layers in such a neural network. So according to Sabinko, who proved that in 1989, he proved the theorem that states that we don't need more than two hidden layers. So this is pretty important. With no more than two hidden layers, we can represent any arbitrary region, assuming a sufficient number of neurons in the hidden layers. Given any data, we are ensured to have a function that actually is represented by a neural network. So that's pretty powerful result, from the perception that we can model anything that is linear. So if we have data like this, we could find this decision boundary with just no hidden layer. We know that if we have actually data that is look like the XOR function, something like this, it's possible to model it with another continuous function. But also, what is this result is telling us is even if we have data that has, let's say, some pluses here, some minuses here, some pluses in here, then we could model any discontinuous function. So we could find a decision boundary that actually will isolate these points here, or maybe do something like this and something like this, and maybe something like this if we have positive points here, etc. So if for any configuration of data, we will be able to find neural network, assuming you have enough neurons in the hidden layers and you do enough training to find this sweet spot of weights that actually map the input to the output.